Hello everyone and good morning. Welcome to the OneClass channel. My name is Fejiro and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today I'll be going over some commonly asked chemistry questions and I'll be doing my best to cover them, and these will be both at the high school and college levels. If you have any homework help, or you want to go over some tutoring, or you want to go over and further clarify some of the topics we covered today, please don't hesitate to click on the link in the description below. That way we can further assist you with our wonderful professional tutors that we have here. With that being said, let's get ready to start with the first question for today. So for today, we're going to start with this question. What is the electron pair geometry and shape of the molecule CH2O? Electron pair geometry and molecular geometry of CH2O. So in order to find this out, we first need to draw out our Lewis structure. We have CH2O, which I'm not sure what it's called, but I can see the formula, the molecular formula, thankfully. So with that, we're going to try our best to formulate a Lewis structure from this. Okay, so we have one carbon, two hydrogens, and one oxygen. Carbon has 4 valence electrons, oxygen has 6 valence electrons, and the hydrogens add 1 each for the valence electrons. So in total, we're working with 12 electrons, okay? And now because carbon has the most unpaired electrons, we'll put that in the middle, okay? And now let's make it have a bond on each side. So now we have hydrogen, hydrogen, and oxygen. Now right now carbon is sharing 3 of its 4 electrons, so we're going to add a 4th one right there. And oxygen is sharing 1 of its 6, so it's going to be 2, 3, 4, 5, 6. Now, as you can see, we still have 2 unaccounted for unpaired electrons. So what I'm going to do here to get rid of them is add them to the bond. So now what I have is this. Okay? This is currently what I have for the Lewis structure, and then we're just going to add the electrons. And as you can see here, not only should we have 12 electrons, but at the same time, we should also have a formal charge of 0 for everything. So let's verify the electrons first. Carbon, okay, has as its, the electrons, not the formal charge. We have 4 bonds, so that's 8 electrons so far. And then oxygen has 2 lone pairs, so that's 4 more electrons. So that's 9, 10, 11, 12. So the electrons are a check, okay? And now, let's see about the formal charges. Hydrogen, its formal charge of 0 is when it has just 1 bond. So we're good. Carbon's formal charge of 0 is when it looks like that, 4 bonds. And that is what it has. The double bond does count as 2 bonds. And now for oxygen, for it to have a formal charge of 0, it needs 2 bonds and 2 lone pairs, which is also what it has here, since the double bond counts as 2 bonds. Now here they're asking for the electron pair geometry and the molecular geometry of this molecule, okay? So this right now is what we have for the Lewis structure. The electron pair geometry is based on its hybridization, also known as the amount of pairs it has attached to, whether it's bonding pairs or lone pairs. So for this, we're going to circle how many pairs is on the central atom. We have 1, 2, and now here's the tricky part. A double bond still counts as 1 bonding pair. Okay, it's just a specific type of bonding pair. So we're going to actually label this as the 3rd one. So because it's 3, this is actually sp2 hybridized in the central atom, okay, because it has 3 bonding pairs. And because we can say that, this electron geometry is known as trigonal planar. Okay, that would be the electron pair geometry. Now to find out the molecular geometry, so I'm going to write this down next to it, the electron pair geometry. To find the molecular geometry now, we need to see how many of these pairs are lone pairs, okay? And luckily for us in this case, there are no lone pairs. So we can actually say that the molecular geometry, because it's just 3 bonding pairs and 0 lone pairs, so it has distribution of 3, 0, the molecular geometry stays the same as the electron geometry actually. This is also known as trigonal planar. And what does this mean in regards to the shape of the molecule? You see how I drew it there in the Lewis structure? That is close to what it would actually be when it's just floating around in the environment. If whether it's liquid or solid, the molecules will actually take the shape of trigonal planar to where every atom from the carbon is around 120 degrees apart. That is what it means to be trigonal planar. And it's planar because it's all on the same plane. This would be flat pressed against the plane. Okay? So that would be the electron pair geometry and the molecular geometry of CH2O. So let's see what they have here. Yep, that's what we got for the Lewis structure. And it is trigonal planar for the electron pair geometry and the molecular geometry. So this is correct. So now for question number 2, we have name the following compounds. We have quite a bit of them, but our goal here is to name them. So the first one we have is Li2S. Okay? So what I like to do here is that I like to figure out if it's an ionic or a covalent compound. So for that, we have to look at our periodic table. So Li2S, that is a lithium and a sulfur. Okay, and lithium is a metal, and sulfur is a non-metal. So this is definitely an ionic compound. Okay, so that being said, we can now write at least it's going to be lithium sulfur. Okay, but we're not done quite yet. That is just what I like to do at the start. Okay, because whether it's an ionic or even a covalent compound, it's important that the ending gets changed. Okay, the last part, the suffix for sulfur gets dropped, and instead it will be sulfide. This is what we would have for Li2S. It would just be lithium sulfide. Okay. Now let's move on to the next one of what we have to name. We now have SNO2. I'll just list out all of them right now. Okay. K2O. Number 5 is Ba3N2. So SNO2. Same thing here. We gotta figure out if it's an ionic compound, because it does change the naming rules a little bit. Just like how with lithium sulfide, we didn't specify how many lithium we have. You don't typically or even ever see that for ionic compounds. We just say what they are. Okay? So SN is, I believe it's a transition metal. If I can, nope. SN is tin. So this is tin, and then we have oxygen. Okay, so now this one is a little bit tricky. It is one of the transition metals, or specifically a post-transition metals. So it actually has different, as they call, I guess, oxidation states. It could be, I know like one of them is like tin 2 and tin 4. But let's see, we're going to base it off the oxygen, okay? So the oxygen, similar to the sulfur, will end in oxide, but what we're trying to figure out is the tin part. Oxygen has 6 valence electrons, and to fill this octet usually just needs 2 more electrons. So we're dealing with O2-, okay? That is what oxygen likes to do. It's like one of the things you can base it off of if you want to be safe. But it's saying here we needed 2 of them in order to balance this tin out to make a net charge of 0. So if we need 2 O2 minus, we had a 4 minus charge. So tin had to be 4 plus. So this tells us actually what type of tin we're using. And we actually use the Greek letters here. The Roman letters. Yes, the Roman letters, sorry. And it'll be tin, and the C is 4, right? So it'll be tin, 4, oxide. That will be how you name this compound, okay? Because tin exactly can go through different states, and we need to specify which type of tin this is, okay? And now the same thing, we have Rubinium Bromide. Luckily for us, rubidium is just on the first column, so that means it's just going to be +1. And bromine, exactly, it's on the 17th column, so that's -1. So we really just have rubidium, and not bromine, but bromide again. See how the ides keep being there? Because that's one of the most important rules when it comes to naming these compounds. And rubidium. Hopefully I spelled it right. Yes, I did. And now K2O. Same thing here. We have potassium, which is 1 plus, and oxygen, as we saw, was 2 minus, and it just bounces out. We can just say potassium oxide. Okay. And now for the last one, we have Ba3 and 2. Lucky for us, exactly, it's a face value again. We have barium, which is a metal, and nitrogen, which is a non-metal. And nitrogen does have -3 because it needs 3 more electrons to fill its valence shell, and barium does have +2 because it needs to get rid of 2 to have it's close to its octet. So with that, that's how we got the 3 and the 2 here, because we need 3 bariums, 2 nitrogens, so each one will be +6 now and -6 to have a net charge of 0. But we can just call this barium instead of it being nitrogen, we drop the ogen part and it's nitride. Okay, so all of these technically was a metal versus a non-metal. Okay, the only tricky one was tin, because post-transition or even transition metals do function a little bit differently when it comes to the naming rules. Okay, so with that being said, let's go back to this and we'll see how we did. So lithium sulfide, they do say this one is just tin oxide. Let me check the periodic table just to see. I can see how it is just tin oxide. That one is a little bit tricky. Rubinium bromide is correct. Potassium oxide and barium nitride. So with this, just because I want to make sure that it is 100%, the tin oxide may just be the name because it's on the 14th column, to where tin is always 4 plus. I am not sure if I've seen tin 2 plus, but let's see if we can find that. Tin 4. So that is the name that is given. This is one of the tricky parts about the naming, is sometimes there are more common names and there are more specific names. But let me see if there is even a tin. Let's see what tin 2 iodide looks like. So there are different states for tin. So technically the most correct answer would be that. The only issue with this, which is what I do recognize, is that on the periodic table, just like how you don't really specify for carbon, tin doesn't really get specified for. I mean, tin, with that logic, because it's on the 14th column, shouldn't really get specified for either. But that's why I do stress the whole transition metal. Tin is technically a transition metal. Well, as you can see here with the coloring, it's known as a post-transition metals. And those things do pose a chance of having different oxidation states or different charges of what ions they could form. So in this case, although tin oxide is a possible answer, to avoid confusion, on which type it would be, I would specify still that it's tin 4 oxide, just because we always want to be as specific as possible when it comes to these transition metals. Okay, that's the only thing I would say here. So this is still correct, but I would have tin 4 oxide to be more specific. Okay, so yes, transition metals can be tricky. Watch out for those, and hopefully you do great. Question number 3, we have draw the Lewis structure for chloroform CH3CO, CHCl3, and what are its electron pair molecular geometries, and what orbitals on the CH and Cl overlap to form the bonds involving these elements. Okay, so this one's a little bit tricky, but we have CH3Cl. Let's say it's so Lewis for CHCl3, okay? And electron pair geometry and molecular geometry. And we also want to know what orbitals overlap. So, with this being said, let's first knock out the Lewis structure first. CHCl3, we have 1 carbon, 3 chlorines, and 1 hydrogen. So, that is 4 valence electrons plus 1 valence electron. That's 5 right now, plus 7 times 3, because there's 3 chlorines. So that's 21 plus 5. We're working with 26 electrons total. We put carbon in the middle again because carbon has the most unpaired electrons. So carbon. Oops. H. Whoops. Apologies. Cl. H. Okay. And now let's go ahead and fill in the rest of the lone pairs. Hydrogen is completely satisfied being like that. Same with the carbon because it's already sharing 4 of its 4. Now the chlorine is now sharing 1 of its 7, which is why you need to add 6 more. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay. And now let's check if we have the right amount of electrons. So around each chlorine is 6 more, and we have 4 bonds. So that's 4 times 4. Oops, sorry, 4 bonds. So that's 4 times 2, which is 8. And then 6 times 3, which is 18. So 18 plus 8, that does indeed equal 26. So we're done with the electrons. We got that. That's good. The formal charges for each one, just to make sure. Carbon having a net formal charge of 0 looks like that, or just 4 bonds, which is what we have. And chlorine's formal charge of 0 is when it has 3 lone pairs and 1 bond, which each chlorine does have. And the hydrogen's formal charge of 0 is just when it has 1 bond, which is also what this looks like. So we have a formal charge of 0 throughout. So this indeed would be our Lewis structure for this. And the important thing is that yes, everything does follow the octet rule when it's applicable. Okay? So now it's asking for the electron pair and molecular geometries. Once again, let's look at the bonding pairs it has, or just pairs in general, and how many of those are bonding pairs and how many of those are lone pairs. So we have before we continue, this is all in reference to the central atom. So 1, 2, 3, 4. So that's 4 bonding pairs, okay? And 0 lone pairs. So right now we actually have enough information to say the electron pair geometry and molecular geometry. For the electron pair geometry, we just take the total of it. So 4 plus 0, so that's just 4 pairs in total. Okay, so we know that this is sp3 hybridized, and this would be tetrahedral for the electron geometry. And now for the molecular geometry, we just specify now what the breakdown is. As we said, we have 4 and 0. 4 bonding pairs, 0 lone pairs. So funny enough, the molecular geometry is also tetrahedral. Okay? And now the last question asks, which orbitals overlap? Now this one is a little bit tricky, okay? So for this, we can say that for the hydrogen to the carbon, because hydrogen only has the s orbital, it's an s, and because the carbon, as we said, was sp3, I do believe is an sp3 overlap, and then the rest of them, the chlorines, are all just overlapping sp3. Now for this one, I'm most likely wrong, so I will refer to the colleague here to see exactly what they're doing. I know it's something like this, but I don't want to be leading anyone astray. We have exactly this. We have the Vesper theory is tetrahedral molecular geometry, and the electron pair geometry is tetrahedral. So that one is correct. Now each CCl bond is formed by the overlap of sp3 hybridized orbital on the C atom with a 3p orbital on the Cl atom to form a sigma bond. So it's not just sp3 for everything, it's sp3 with 3p. So this is for the carbon side, and this is for the chlorine side. And for the carbon hydrogen, the sigma bond is formed by the overlap of sp3 orbital on the atom with a 1s orbital. So we were close, but now it's important to talk about what this means, okay? So what is hydrogen when you look at the electron configuration? We have just 1s1. This is what it means. And for the carbon, the reason why it's sp3 hybridized, that's what we call it, is because of the bonding pairs around it. Okay, so that is the state it's in, which is why the 1s and the sp3, those are what's communicating. Same thing, because all the bonds are the same, that's what carbon is using to communicate with the chlorine as well, which is why here it stays sp3, okay? But if you look at now the electron configuration for chlorine, we have it, actually, as you can see here on the periodic table, it is on the 3rd row, which is why it's 3p, because if we actually did the shorthand notation for it, it'd be neon, and then you go 3s2 3p 5. And I'm probably wondering how they know that it's bonding from the p orbital. So for these, we usually assume that exactly we're trying to build from the bottom up. The s orbitals are closer to the nucleus, well, the center of the atom, and so the s orbitals get filled first. Think of the s orbitals on the chlorine as like maybe any 2 of these electrons. Those are probably what the s orbital. It's already filled. So what it was trying to do was fill up its p orbital. Hence how it had 3p5. And what carbon did was say, hey, I can help you fill those out if you share this electron with me. So while this carbon is sp3 hybridized, that is why it's attached to the 3p and not the 3s. So overall we learned it was 3 from the fact that it is its most outer shell, that is the valence electrons, and it's going to be the p orbital because we said we fill from down up, the lowest energy to the highest energy, and the p was the outer energy to which carbon is going to attach itself to. Hopefully that made more sense in regards to now how they got the answer. It was just hard to get the phrasing out, but I'm just glad we had this basis in order to do so. So now with that being said, let's move on to question number 4. We have draw the Lewis structure for methanol, okay? And then we have based on the structure, predict the HCH bond angle. And then we also want to predict the HOC bond angle. And we want to explain our reasoning for both. So first we have Lewis for methanol, which is H3COH. So now methanol is a little bit tricky because we have to know that we're adding a hydroxide group. The reason why I say that is because the best thing to start with is just drawing the methane. Okay, I know that we're adding extra steps, but if we just jumped right to drawing the methanol, we would most likely end up confusing ourselves. Okay, so with that being said, we have CH4 for methane. Okay, that is 4 valence electrons for carbon and 1 each from hydrogen. So we are working with 8 electrons total. This is for methane, and we have it like this. Okay, and this is balanced out. This is the Lewis dot diagram for CH4 methane. Okay, now an alcohol, just like how we have for methanol, is when a hydroxide group gets added. It replaces a hydrogen. What is a hydroxide group? This is known as the OH minus group. Okay, that is a hydroxide. So what it's gonna do here is that any of these hydrogens here gets replaced by an OH. So I'm actually going to copy this and paste it, because what we're going to do now is replace one of these with the hydroxide group. So right here, we're going to write OH. And you notice, bam, we actually have the Lewis for H3COH. It was just important we started with methane, so that way we wouldn't try to, make all the atoms go around the carbon, because that would just confuse us, which is why I like to first draw that structure first, specifically methane. For these type of questions, it is important that you understand the original hydrocarbons we're working with, so there is a little bit of familiarity with the naming and the IUPAC rules. That's how I was able to get here. So this right now is what we have for the Lewis structure, and make sure we add in our electrons, and we can actually verify to see if everything is correct. So first of all, how many electrons do we have total here? For methanol, we would have 3 electrons we can work with, plus 4 from the carbon, plus 6 from the oxygen, and then another one from hydrogen. So that's 4 plus 4 plus 6. We need 14. And if you count, we have 1, 2, 3, 4, 5 bonds. That's 10 already electrons. And then 2 pairs each on the oxygen. So this does indeed add up to 14. And if you compare the formal charges, hydrogen's net formal charge of 0 is when it just has 1 bond. Carbon is when it has 4 bonds, and oxygen is when it has 2 bonds and 2 lone pairs, which it does indeed. So this is actually balanced with the electrons, the octet rule, and the formal charges. This is the Lewis structure for methanol. Now the question is asking us, based on this structure, predict the HCH bond angle. Okay, so they're looking for like a bond angle of one of these. So in order to do that, we first need to understand what type of bond we're dealing with for both of these. Okay, so we're going to make each, the carbon and the oxygen, our quote-unquote central atom. Starting with the carbon, we have, it has 1, 2, 3, 4 bonding groups. Okay, well, 4 bonding pairs and 0 lone pairs. So that would be, we just write it as 4, 0. The electron geometry would be tetrahedral, and the molecular geometry, based on the fact that it's a 4-0 split, 4 bonding pairs, 0 lone pairs, it's also tetrahedral. The electron geometry is based on the total, which is just 4, which is why it stays with the name tetrahedral. And the molecular geometry breaks it down of like, okay, now which one of each do we have? So with that being said, we can now take a closer look at this in regards to, just to make sure we have everything. Tetrahedral molecular geometry looks kind of like this, where one is going into the page, one is going out of the page. But overall, all the angles that they have there is around 109.5 degrees. That is like, because it's a 3D structure, that is a perfect distance they can have from each other to where everyone is equally distanced from themselves. So when it asks the question, predict the HCH bond angle, that includes one of the HCH. So if I said this was H, and the carbon was in the middle, that would be the bond angle there. So for B, bond angle will be 109.5. Okay, and reasoning being because of the tetrahedral shape. All right, for the molecular geometry specifically. Now, if we look at the oxygen, this one's a little bit different. We have, let me just erase these so there's no confusion. We have 1, 2, most wrong color. We have 1, 2, 3, 4. So now with this, although we have a 4 total, so it's also going to be tetrahedral for the electron geometry, we have 2 bonds and 2 lone pairs. So although for the electron geometry it is tetrahedral, the molecular geometry is known as bent. And what this does is that if we drew it as well, like the 3D structure, we kind of have the oxygen here and the 2 H's. Okay, and what's happening here, the reason why it's called bent, is that not only does it try to mimic the tetrahedral shape, but it really doesn't. What happens here is that because of the lone pairs, it kind of exerts angled force on it. So instead of it being that 109.5 like the other tetrahedral, it actually squishes it a little bit. So all we can say, we don't know the exact amount, but we can say that it's going to be less than 109.5. So for C, it's less than 109.5 because the molecular geometry is bent. We don't know the exact amount. It's not too drastic. We're not saying that it's 1 degree. We just know that it's not exactly 109.5 because the lone pairs don't have like an even distribution split with the other atoms attached. They actually do exert a force where they kind of push things in a little bit closer. So that's what we're dealing with here. B, 109.5. C is just less than 109.5 for the bond angles based on the structure of their geometries. So let's see how we did. Exactly. So this is what they have here as well for methanol. And they say it has 4 bond pairs and lone pairs. So the electron geometry is tetrahedral with bond angles of 109.5 degrees. I would actually use molecular geometry because now we'll see if they got the right answer for the next part. So it says 4 electron groups, and that's what I was afraid of here. They based it off the electron geometry. It is tetrahedral as well for the electron geometry, but the bond angles, like I said, although it'd be close, it wouldn't be exactly 109.5. It'd be a little bit less. So the only thing I would say here is that technically what they're saying isn't wrong except for the bond angle part. If you were asked this question and you're given some choices and A said 109.5, B said less than 109.5, for the oxygen one, the most correct answer would be B. Because if this person had drawn the molecular geometry instead of referring to electron geometry, I think they would have noticed that the bond angles are just slightly less than 109.5. Because although the electron geometry is tetrahedral, the molecular geometry, as you can see here, from the 2 lone pairs and the 2 bonds, it is going to be bent. So, bent molecular geometry for COH means that it's less than 109.5, not 109.5 exact. So, with that being said, although everything else they did was fantastic, these are just the little things that can make you, for example, get the question wrong, because you just have to recognize that part when it comes to the molecular geometry. So question number 5, we have, we want to draw a valid Lewis structure for tetrafluoroethylene, okay, C2F4. And the industrial starting material used to prepare Teflon, and Teflon is used for most, I'm not even sure if it's used anymore, but the goal here is that we want to draw this Lewis structure. So we have Lewis for C2F4, okay? And we have to assume that each carbon is bonded to 2 fluorine atoms. So let's see here. How many atoms do we have total? 6. 2 carbons, 4 fluorines. So with that being said, we're actually going to do, let's see, carbon has 4 valence electrons. So that is 4 times 2, because there's 2 of them. So that's 8 electrons there. And fluorine has 7 valence electrons. So that's 4 times 7. So that's 28 plus 8. We have 36 electrons in total we need to distribute. All right, so as I said, we're going to keep the carbons in the middle, just bonded ones to each other. And we're going to go like that, because we do not know the shape yet. Actually, you know what? I'm going to put it like this for a reason, as you'll see later, because I do know the shape. So this will make more sense when we do actually do what we're about to do. So with that being said, let's fill out the valence electrons for fluorine first. So fluorine right now is sharing 1 of its 7. So we have 2, 3, 4, 5, 6, 7. Complete octet. Same with every fluorine here. They should have a complete octet. Okay? So now, what we're going to do here is see specifically what's happening with carbons. Carbons right now are sharing 3 of their 4. So we just have 1 unpaired electron on each carbon. And this is why I drew it like that, because what the unpaired electrons do, they're actually going to form a bond, an extra bond along with that single bond in the middle. So now we have this picture actually for it. A double bond. And like that. This will be the theoretical Lewis structure for tetrafluoroethylene. Okay? And we can actually check to make sure by confirming the number of electrons and its formal charge. So formal charge 0 for carbon is just when it has 4 bonds, and 0 lone pairs, which is what each carbon is doing. The double bond does count as 2 bonds, so that's why we can make this work. The fluorine, on the other hand, has 3 lone pairs and 1 bond, which is what every fluorine is doing here. So this picture is perfect for this. So we can actually say this is the Lewis structure for tetrafluoroethylene. So we have done this based on what the question is asking, but I do want to actually show something really cool in regards to this. This will be considered a perfect structure for a monomer because it has that double bond there. What do I mean by that? I mean that it can actually do this really cool thing to where it kind of keep going like this. And each of them, let's say we only had 4 of them. This is how you can actually have a sheet of, for example, these carbons, this carbohalide, for example, because of the fact that, in a sense, what would happen is that this, I guess, double bond would kind of open as a gate. They would open up, one would open up that way, and one would maybe open up that way, for example. Or it may open up both on the same sides to where they can attach to other carbons that would continue on the chain. So this is actually a perfect example of a monomer, or at least a starting chain of what you would have for a continuous polymer chain of carbons, as I've shown below. I just want to add that fact because this is actually explaining things like Teflon, for example, to where how can you have such a, like, yes, a non-stick surface, so it's very hydrophobic, if that's the right word. Yes, exactly, non-stick surface. So it's really just prevents materials from going through and stuff. Is because when they actually do bond together and form this polymer, it's this beautiful sheet like that. But nonetheless, this is the Lewis structure for that. So see how we did, and voila, this is what they have as well. This would be the Lewis structure for C2F4. Now question number 6. We have draw a Lewis structure for XeOF4. So Lewis for XeOF4. So this is where it gets a little bit tricky, because xenon is actually a noble gas. It has no reason to even, or at least a noble element, it has no reason to even make these bonds. It really doesn't serve that purpose because it's a filled octet already. It has 8 electrons. But nonetheless, nature is imperfect. Things do bond that don't really make sense. As long as other rules are satisfied, it gets a pass. With that being said, xenon can contribute 8 electrons from that. Oxygen, 6 electrons. Fluorine, there is 4 of them. So although it's 7 electrons, it's 7 for each of them. So that's 28 in total. So in total for all of this, we have 8 plus 6 plus 28. We need to account for 42 electrons, which sounds daunting, but I know we can do it. So we have xenon in the center, okay? And now, right away, we're really just going to break this octet. We're going to have it as 1, 2, 3. Let me start like this actually. 1, 2, 3, 4, 5. There we go. A little bit more spread out. That's good. All right. And now we have OF4. So we're going to have O, F, 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 F. Okay. So that part is done. Now, fluorine is currently sharing 1 of its 7 electrons. So we're actually going to fill out this octet first. It's the easiest one so far. 3, 4, 5, 6. Well, that's 6 of the 7, so we're good. And the same thing here. 2, 3, 4, 5, 6, 7. And 2, 3, 4, 5, 6, 7. And 2, 3, 4, 5, 6, 7. So we're done with that part. Now, oxygen right now is sharing 1 of its 6. So it's going to be 2, 3, 4, 5, 6. Xenon right now is sharing 5 of its 8. So we're going to have 6, 7, and 8. So right now we have 2, okay, unpaired electrons, 1 on the oxygen, 1 on the xenon. So what's actually going to happen here to satisfy this part, we're actually going to throw them into an extra bond with the oxygen and xenon. So actually what we have for this is going to be now, if we redrew it, okay, we're going to split it perfectly into 6, 3, 5, 6. Give it a little bit more space for the lone pair. We actually now have oxygen double bonded, but every other fluorine is still single bonded. And yes, we still have that lone pair on the xenon. So not only does it break the octet rule, I would say it completely smashes it. This is nothing close to an octet rule. So with that being said, let's fill out the octet rule for the other ones, the fluorines. So it's funny how xenon just completely ignores it, but the fluorines and the oxygens around it still obey this octet rule. And to make sure we just drew this the most stable as we can, we're actually going to compare the formal charges for each one. So as we said, oxygen's formal charge is where it has, or at least where it has a net of 0. It's when it has 2 bonds and 2 lone pairs, which is what it has. The double bond does count as 2. And fluorine is when it has 1 lone pair, one bond and 3 lone pairs. So that's good as well. And now xenon's a little bit tricky. Xenon for neutral is just has where it has 4 lone pairs. But we can actually expand this further to where we can actually say, based on the lone pairs, we're not replacing them per se with a whole bond, but we're actually making each one a bond. So we have 1, 2, 3, 4, 5, 6. Because double bonds counts as 2, that's 6 bonds and 2 lone pairs. Well, sorry, 6 bonds and 1 lone pair, which is actually what it has here. So we can actually still argue this has a formal charge of 0 throughout. So this would be indeed the Lewis structure for xenon, oxygen, tetrafluoride. Okay? So now let's see what it says here. Determine if the central xenon atom obeys the octet rule. No, it does not. Okay? Does it have an incomplete octet? If anything, no. This goes way beyond it, which is why we actually use the term expanded octet for the xenon. That is definitely what it's doing. Okay? Now it says identify the number of lone pairs, single bonds, and double bonds on the central xenon atom. So for this, we have 1 lone pair. Okay, we also have, for single bonds, we have 4 single bonds. And we have 1 double bond. That would be for xenon. Hopefully we cover everything for this question. But as you can see, this is an extremely expanded octet. And it's only because xenon, it's already a noble atom. So it really just shouldn't be bonding. So when it does, you kind of just throw the rule book out the window, at least for the xenon. The things surrounding it still want to follow the rule book. But xenon itself, that one is a little bit tricky. So the Lewis structure, as we saw here, perfect. 4 single bonds, 1 double bond, and 1 lone pair. 42 electrons. We didn't even count that, but let's see. How many bonds are there in total? 1, 2, 3, 4, 5, 6, because the double bond is 2 electrons each. So 6 times 2, that's 12 electrons. And then we're going to count up the outside lone pairs. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 times 2, that's 28. And then xenon also has 2 there. Almost missed that. So it's actually 12 plus 30, which is 42. So perfect. We do have the right amount of electrons. So let's see. It is an expanded octet. So that's perfect. Okay. And let's see. We have, where does it say it? 1 lone pair and 6 bonding pairs, of which 4 pairs are shared in 4 single bonds, while the remaining 2 are double bonds shared with the oxygen atom. So with that being said, this is correct. And hopefully you can see how xenon really just expanded completely with the octet. So let's move on to question number 7. We have, which is the most polar bond? So for this type of question, actually, to find out which is the most polar, we just compare the electronegativity. Okay, that is almost word for word is asking, what is the electronegativity difference between these atoms? Okay, so for that being said, I don't even have to look at the periodic table for this. It's a carbon and a carbon. This electronegativity difference is 0. So if anything, this is going to be the least polar bond. If we're going to organize it based on order, we can say that C is going to be the lowest. Okay. And now for B, we have CH, which is, as you can see, going to be relatively low as well. But let's actually now pull up the numbers. As soon as I can move this thing a little bit more down. That's very strange. Well then. So, let's just move on. We have CH, periodic table. Hydrogen has an electronegativity of 2.20. carbon is 2.55. Difference is 0.35. Okay. There we go. That was strange. Okay. And now, for this, we have NH as well. Let's look at the difference, but let's just get everything together. OH and ESEH. Okay? So NH. Nitrogen, on the other hand, is 3.04 minus 2.20. That should be around 80.84. Yep. 0.84 difference. And OH, now we have 3.44 minus 2.20, 1.24 difference. And then for E, the last one, we have SEH. SE is, wow, 2.55. My eyes do not deceive me. That would be the same thing actually as a carbon. So that would be 0.35. So now carbon and selenium, those ones will be a little bit tricky in terms of which is the most polar. So for those ones, we usually just refer to best by size. Luckily for us, that's not what we're asked for. We're asked for which is the most polar. So as you can see here, if we're to organize it, if we just assume that the size did play into effect, it'd be CC, CH, SEH, then it would be NH, and then the winner would be OH, because in this case the most polar one is indeed D, the bond between oxygen and hydrogen. Okay, and as you can see here, all we did was go through our electronegativity difference. So just be aware of that, is that when they're asking which bond is the most polar, typically they're asking for which one has the greatest electronegativity difference. Okay, so let's see what they did. All right. Oh, I guess it depends on the periodic table we're looking at, but they have selenium as 2.4. Interesting. Well, nonetheless, the most polar bond was given as OH. And with that being said, just make sure you pay attention to which periodic table you're using, and you are consistent when you're pulling up the electronegativity. You don't want to be pulling up electronegativities from different periodic tables. As you can see, we have quite different numbers, so it's important to just keep that consistent. Okay, now question number 8. We have draw a Lewis structure of ClF3, so that's, I believe, chlorine trifluoride. And we want to identify the number of bonding and non-bonding electron pairs, and what's the electron pair and molecular geometry of this molecule. So Lewis for ClF3. Okay, so with this being said, we have all of them on the same column, so really it's going to be 4 times 7 valence electrons. So what we're dealing with is 28 electrons total we have to work with. And now for this, because chlorine is a unique one, we'll put it in the middle. Even though they both have the same amount of unpaired electrons, chlorine is the only unique one in this case. So we have Cl, and then we somehow have F3. And you're probably questioning already, how are we going to do this? Because chlorine only wanted one bond, really, because it's only missing 1 electron to have its octet. So I'm going to tell you right now, chlorine is indeed going to break the octet rule. It's going to have to expand. So with that being said, let's fill this out in regards to it. So we have, oh, maybe that's not an L. This is an I, which does change things. The reason why, because as I was doing this, based on this, if I were to draw it out, okay, and I had the F's will be balanced out, but the issue with the chlorine is that it's sharing 3 of its of its 7. So it'd be 4, 5, 6, 7. Oh no, it could work as well. Well, we have to make a casting call here and just assume we're talking about chlorine trifluoride. And I'm going to put carbon as well. That one is just relatively straightforward, where it has the iodine and the 4 fluorines. That works as well. But let's just assume it's chlorine trifluoride. So let's try again. Okay. So, with this being said, we're going to have 1, well, technically it's sharing 1 of its 7. So 2, 3, 4, 5, 6, 7. Same thing here. 2, 3, 4, 5, 6, 7. And 2, 3, 4, 5, 6, 7. Okay. And now the chlorine in the middle is sharing right now 3 of its 7. So it's going to be 4, 5, 6, 7. So that is what chlorine is looking like right now. Okay. So with that being said, it's asking us for the number of bonding and non-bonding electron pairs. Before we do that, let's just make sure this is correct. As we said, we want to work with 28 electrons. Do we have that? We have 3 bonds, that's 6. And then how many lone pairs do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11. So that's 22 electrons because lone pairs have 2 electrons each. So 6 plus 22 is indeed 28. Now we also have to see if this actually does satisfy the, well, not the octet rule because chlorine is clearly breaking that, but the formal charge. So fluorine's formal charge of net of 0 is typically drawn as 3 lone pairs and 1 bond. That is what every fluorine has. Now chlorine would typically be the same thing, where it has 3 lone pairs and 1 bond. But with this expanded octet, what we could do is that each of these electrons in a lone pair could be turned into a bond. So this is all we're going to do here, because to match the picture, we do indeed have 3 bonds and 2 lone pairs, which is what that chlorine has. So everything here does have a formal charge net of 0. So we're good to say this is yes. This is our Lewis structure. Now let's identify the number of bonding and non-bonding electron pairs. We have, based on the central atom, 1, 2, 3 bonding pairs and 1, 2 non-bonding electron pairs. Okay. So with that being said, the way we would write this down is that it has a 3-2 split. So the total of this, in terms of how many pairs it has in total, is just going to be known as 5. That's how we're going to find the electron pair geometry, okay? So with this being said, if I remember correctly, the hybridization for this would be sp3d. And this electron geometry, so the EG, is known as trigonal bipyramidal. If I know how to spell pyramid, bipyramidal. There we go. So that would be that name. Now, because it's a 3-2 split, the molecular geometry actually, this one is known as T-shape for the molecular geometry. What I mean by that is that because the lone pairs, it's kind of going to do this. It's going to be 1 at the top, 1 at the bottom for the chlorine, and they're going to have 2 electrons, and then this is going to stick out like that. Theoretically, this would be the most, I guess, the best structure for it. So if we looked at it at a plane, this is the x-axis, this is the y. The electrons and the fluorine would kind of be on this x-axis, and then the 2 fluorines will stick out on the y-axis. So that's how we kind of have this T-shape, because it kind of goes like that. Okay? That is what I believe, and we're going to actually double check here in regards to the Vesper theory that we have. So we have 3 and 2 split. It is 5, so the bonding groups is 5. Let's scroll down. Electron groups 5, and it is a 3-2 split, and it is indeed known as a T shape, what looks like that. So that's perfect. Okay. So with that being said, let's see actually if we can agree with our colleague as they draw it. So it was indeed chlorine trifluoride. So that's good that we didn't try to solve for carbon. And with that being said, the 5, they do say it's trigonal bipyramidal for the electron geometry. And it does say that it has a T-shaped molecular geometry. So this is correct indeed. So now let's move on to question number 9. We have it saying, a covalently chemical bond is one which, and you have to answer this question. It has, so covalent bond is which, what? A, it says the outer shell electrons are shared by 2 atoms so as to satisfactorily fill the outer electron shells of both. The key word here is being shared. Okay, so far for A, I can agree with what it's saying. For B, it says the outer shell of one atom are transferred to the inner electron shell of another atom. This is just not possible, at least in most cases, because for most atoms, they're working with their outer shells. So even if a transfer were to occur, it would just be transferred to the outer shell of another atom. It wouldn't go into the shell. So that one would not work as a definition. Protons or neutrons are shared by 2 atoms so as to satisfy the requirement for both. So this one is also not it, because of the fact that we're actually trying to share electrons. And this one says electrons are removed from one atom and transferred to another atom so the 2 atoms become oppositely charged. So this one isn't bad either. But the question is asking for covalent bond. What this just described here for D is more of how ionic bonds work, to where there is a transfer to another atom, where it's just like, here, have my electron, and the 2 atoms do become oppositely charged. That's how we have the cations and anions. But that's just it. This is describing an ionic bond, and this would not be it to describe the covalent. So in this case, the best explanation would be A, where the outer shell electrons are shared by 2 atoms to satisfactorily fill the outer shells of both. And I'm glad it doesn't say evenly shared, because we can't make that assumption. So they are trying to share it, but this is where our electronegativity difference plays in for covalent bonds. If the electronegativity difference is great enough, one side would, in a sense, hog more of the electrons than the other. The electrons would prefer to be on that quote-unquote more electronegative side. Okay, if the difference was minimal, like for example, like 2 of the same atoms, then they're evenly sharing it. But exactly, we just know overall that at least it's being shared, compared to an ionic bond to where it's just being donated or received. So A would be the correct answer here. And let's see what it says. A covalent chemical bond is one where the outer shell electrons are shared by 2 atoms to satisfactorily fill the outer shells of both. So they just took straight from what A said. Okay? And that is correct. And it is the sharing of electrons between 2 atoms. And exactly, that is how A is the best choice here. And now for question number 10. Let's see what we have. We have question 10. What is a balance equation for the chemical equation shown below? So this would be, looks like most like a combustion equation, because we have a hydrocarbon reacting with water to form carbon dioxide. Hydrocarbon reacting with oxygen to form carbon dioxide and water. So C3H8 plus O2 turns into CO2 plus H2O. So typically what you would see, at least a full thing if I were to go in detail, is that this is usually like heat is involved somehow, because this is what you call combustion reaction. Okay, With that being said, though, the way I like to balance this out is that I like to compare and see specifically where we have. Let me give it some space for me to actually balance this. Nope. Maybe I can just write it under it, but I'll try to squeeze in the numbers and then rewrite it after. So, based on the products and the reactants, I like to start with the carbons. How many carbons do we have in the reactants? We have 3 carbons. So in order for it to balance out here, we need at least 3 carbons there. Now, for the hydrogens, because exactly there's only one place it goes to, right now we have 8 hydrogens, so we need 4 H2O for it to have the same 8 hydrogens. Why did I not balance the oxygen? Is because based on the products and reactants, it goes from being in one place, here the O2, to 2 places in the CO2 and H2O. Trying to balance that out through just the reactants would be really confusing. So based on what we just did, we actually now compare how many oxygens we have on the product side to make sure the reactants can balance out. So we have 3 O2, so that's literally just 3 O2 right here. And now we have 4 H2O, so that's 4 O, also known as 2 O2. Okay, so 3 plus 2, theoretically we should have 5 O2 there. So this balanced equation should be C3H8 plus 5 O2 turns into 3 CO2 plus 4 H2O. And now we can double check and just list out under it. So we do indeed have 3C, 3C. We do indeed have 8H, 8H here. And now for the oxygen, 5O2 should be 10O. And we're going to see 3 times O2, so that's 6, and 4 plus O, that's 10. So there's 10O indeed. So this is perfectly balanced out for this combustion reaction. Let's see how we did. So we have C3H8 plus 5O2, 3CO2 plus 4H2O. Perfect. So that is the balanced equation, and that is what we had to do for this question. Alright, so now let's move on to question 11, but before we do that, let's take a quick water break. Okay, see how we're doing. Okay, stream is going well, hopefully no issues. And now let's move on to question number 11. We have, give the electron configuration. That's very strange. Yeah. Hopefully this thing didn't just die. Okay. Interesting. Give me a brief second just to make sure this can work. Okay. Alright, and we're back. Sorry for the interruption, but I just want to make sure that my pen was working. So now it says give the electron configuration of Ni2+. Okay? So in order to do this question, we're actually going to first give the electron configuration of just nickel. Okay? So nickel, as we look in the periodic table, is the, if we can find it, 28th atom, and 28th element on the periodic table. So as we're filling this out using the off-ball principle, we have 1s2, because we're just going through the periodic table starting from the top, okay? Because it's going to fill from the lowest energy level all the way up. So hydrogen and helium, that's 1s2. Then lithium, beryllium, that'll be 2s2. Then from boron to neon, that's 2p6, okay? That's now in the p orbital. Then we go back to the s orbital for 3s2. Then we have 3p6. And then we're going to fill in the potassium to calcium. That will be 4s2. And then we enter the transition metals. This right here is a d orbital. And we have 3d8. Okay. That right here would be electron configuration for nickel. And to make sure we have the right one, all these superscripts should add up to 28. So we have 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 8. 28. Perfect. So we have done the electron configuration for nickel. Now for nickel 2 plus, what's happening here is that it actually wants to just shave off its outer shell. So in this case, the outer shell is going to be the one with the highest coefficient. And so we can actually eye it and see that it's 4s2 because that's 4. And funny enough, it actually just has 2 convenient electrons right there. This is what we cancel out. So we'd actually write 1s2, 2s2, 2p6, 3s2, 3p6, 3d8. This right here would be the electron configuration for nickel 2 plus. We wouldn't shave off from the d orbital because technically that is still from the orbital before the 4. Okay? So that 4 is what's going to get rid of the 4s2. Let's see if we're correct. Exactly. We have 1s2, 2s2, 2p6, 3s2, 3p6, 3d8. So this is perfect. And now we can move on to the next question. So question number 12, we have what is the name of Br2O? So for this, we have to first review what type of molecule this is. So with that being said, we have a bromine, well, 2 bromines and 1 oxygen. So that is both nonmetals. So this is going to be a covalent compound because there's no metals present. This is a nonmetal bonded with a nonmetal, okay? And because of that, it does have slightly different naming rules, okay, to where we actually have to indicate how many of each we have, okay? So with that being said, we have 2 bromines. So we have, if we write it out, dibromine. Okay, that is what we're going to start with. All right. And now for the oxygen, even though it's only one of them, because this is now the second part, I guess the anion or just the second part of the name, we still have to specify typically how many oxygens we have. And in this case, we only have 1. So it'll be dibromine monoxygen. And now there's a reason why I wrote it like this, okay? Because this isn't complete yet. The thing I want you to always recognize is that even for covalent compounds, we are dropping the oxygen part and adding the IDE. Now this right here should be the name for that molecule. It should be dibromine monoxide. Okay? So with this, let's see what choices we have. We have bromine 1 oxide. Bromine is not a metal, so not even a transition metal, so it would definitely not have that. We have bromine oxide. Once again, not a metal in any of them, so they cannot go by the ionic naming rules. dibromine monoxide. So considering that it's literally exactly what we got, we can kind of say it's C, but we're still going to cross out the other ones to C. Bromate. That is definitely not it. Because bromate would actually be an ion typically, and it would be something like BrO3 or something like that. If I were to think about it, I don't know off the top of my head what it would be, or maybe it would be BrO4, BrO4 minus, something like that. That'd be probably what we're looking at for bromate. But all I'm saying, that's definitely not it. We would not have bromate there. And bromine 2 oxide, once again, this is implying that it's a transition metal, which it is not, so we're not going to pick that either. So C is really the only choice you can pick here because it is a covalent compound. So, as we said, the name is dibromine monoxide. So this is correct. Now for question number 13. We have, what is the Lewis structure for TeF4? Well, I mean, unfortunately, we have the answer right there, but I'm still going to describe it. So, Lewis for TeF4. So if we can just ignore that answer right there staring at our face, because that is drawn quite big, we're still going to go through the periodic table and see how we got that Lewis structure to begin with. So tellurium, which is Te right here, is on the 16th column. So we're going to assume that it has 6 valence electrons. And fluorine is on the 17th column. So each fluorine will be having 7 valence electrons. So that's 28 in total. And 28 plus 6 should equal 34 theoretically. So we have 34 electrons to distribute. Considering that tellurium is the only unique one, that's what we're going to put in the middle. So we have Te. I can tell you right now, this is most likely going to break the octet rule, because just like oxygen, typically all it needs is 2 bonds to be able to fill its octet, but now it has to deal with 4 bonds. So something is definitely not right here. So we're going to have 1, 2, 3, 4. And now I'm going to fill the octet for the fluorines first. So each fluorine right now is sharing 1 of its 7. So it's going to be 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. And 2, 3, 4, 5, 6, 7. So there we go. We have fluorine complete. Now tellurium, as I said, is definitely going to have an expanded octet rule, because right now it's sharing 4 of its 6. So really we need to add a 5 and a 6, which is what we're going to do. 5, 6. 1 lone pair for tellurium. So with that being said, do we have 34 electrons total? Well, let's check. We have 4 bonds, so that's 8 electrons so far. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lone pairs. So that's 26 electrons again. So 26 plus 8. Hopefully we also do get 34. So this actually has the right amount of electrons. Now, are the formal charges all 0? Let's find out. For fluorine, the formal charge should be 0. We just need 3 lone pairs, 1 bond. And there you have it. That will be the formal charge for fluorine. It is indeed 0. For tellurium, on the other hand, this is a little bit tricky. If we're assuming it works like oxygen, it should actually just have 2 lone pairs and 2 bonds. But the interesting and cool thing is that you actually turn a lone pair into a bond each, as in 1 lone pair would produce 2 bonds, and you would still keep with the same formal charge of 0. So if we did like this, now we have 4 bonds and 1 lone pair, which is funny enough, exactly what tellurium has. So tellurium also has a formal charge of 0. And with that being said, we verified the electrons, the formal charges, and we had to expand the octet for tellurium, but this would be the Lewis structure for tellurium tetrafluoride. And let's see, as we saw here in this picture, that is exactly what we get. So this is correct. And now we move on to question number 14. For 14, we have draw the Lewis structure for pH 3. So phosphorus trihydride. Not really sure about the name, but we do want to draw a Lewis structure. For pH 3. So for this one, we're first going to see how many electrons we have in total to work with. So phosphorus is on the 15th column, so that's going to be 5 valence electrons. Hydrogen is on the first column, so that's 1 each. So 5 plus 3, we need to work with 8 electrons, okay? And now for this one, because phosphorus has the most unpaired electrons, we'll put it in the center, so P. And then we have 1, 2, 3 for the H's. So right now we do have that pH 3. Now let's fill in the rest of the electrons. Hydrogen is already done. It's sharing one of its 1, so we don't have to add anything there. But phosphorus is right now sharing 3 of its 5. So we're going to have 4, 5. And now let's check. Do we have 8 electrons total? Well, we do have 3 bonds, which is 6 electrons, and 1 lone pair, which is 2 more. So 8 electrons, check. Does this have a formal charge of 0 for each one? Hydrogen's formal charge 0 would be when it looks like that, just 1 bond, which each hydrogen does. And phosphorus, funny enough, is when it has 1 lone pair and 3 bonds, which it also has as well. And does this satisfy the octet rule for those that are viable? Phosphorus octet rule is indeed satisfied. So this right here would actually be the Lewis structure for pH 3. Now let's see how we did. And for this, what they actually did was go ahead and draw it in the, I guess, the 3D structure of the Lewis, to where we have one of the hydrogens, the thick, I guess, triangle that's filled in is one that's coming out of the page towards us, and the one that's dashed, that's the one that's going into the page away from us, okay? And so that's how they chose to draw it. Although this one I drew as well would be a perfect Lewis structure, if they asked for like the 3D Lewis structure for it, this is what they would, what we would go with, okay? Nonetheless, though, they're both correct. It's just very important that if it did ask for a 3D structure, then mine would not be satisfactory. You want to make sure you have that solid line to indicate the one that's coming out of the page, and a dash to indicate the one that's going into the page, okay? So now for question number 15. We have, what is the Lewis structure of NaOH? We want to fill the octets with lone pair electrons and assign a formal charge if available. Well, as you can see, the Lewis structure is right in our faces. It says it's Na single bond with O, single bond with H. But now let's see, how did they get that? So Lewis for NaOH, okay? So with this being said, we can actually approach this 2 ways, but what I'm going to do is approach it the way of the hydroxide starting there. So funny enough, hydroxides, okay, this is something you have to memorize because it occurs very frequently, is known as the OH minus. How do you draw the Lewis structure for this? So oxygen has 6 valence electrons, hydrogen has 1 valence electron, and the minus indicates we add 1 more electron. So in reality, we have OH like that bonded, and then we have like that. This right here will be the Lewis structure for OH minus, okay? Now, what happens here is that sodium, okay, because it always, like as an ion, it got rid of 1 electron, it would just be Na plus. This Na plus can actually just go right here and just attach itself, because Na plus has no what's it called? Na plus has no valence electrons because they got rid of it. So that's how we can just kind of slide it right there. And this actually would be the Lewis structure for NaOH. Obviously, you convert that electron to a bond, but even then, I actually leave it like this only because NaOH, that's when we are working with ionic, a metal and a non-metal. So in this case, this is actually what we would get, NaOH. So now in regards to this, it asks us to fill the octets with lone pair electrons, which is what we've done. And it's also asking us to assign a formal charge if available. Okay, so let's see what formal charges we can do. So if we redrew this to where it just has NaOH, okay, we can actually now say that, all right, so what is the formal charge for each one? Sodium by itself, theoretically, we just have one bond, which is what it's doing there. So its formal charge is 0. That one's good. Oxygen, on the other hand, would like to have 2 bonds and 2 lone pairs, which is also what it's doing, so it is satisfied. And hydrogen, the last one, just likes to have just 1 bond, and that's also what it's doing. So this, all the formal charges would be 0, okay? Now, for the last part, let's make sure we have the correct amount of electrons. So hydroxide, as I said, we're working with 8 electrons. Now, funny enough, when you actually look at NaOH, it'd be the same thing. Sorry about that. Just trying to close this, but this won't close. There we go. So with that being said, NaOH, if we actually went through that as well, we have Na contributing 1 electron, oxygen is 6, hydrogen is 1. It actually is also working with 8 electrons. As you can see here, we have 2 bonds, which is 4 electrons, and 2 lone pairs, which is another 4. So the Lewis structure for this would indeed be that. Okay? And that is what we have. Formal charges are all 0, and it is indeed NaOH. But funny enough, I still like this picture better because when you do put this in a solution like water, we have the Na plus by itself and the OH minus. And the reason why it's like that because the oxygen, this is what you call Ionic Shift. So the sodium actually did just pretty much give its electron to that oxygen, which is why we have the OH minus. And funny enough, this would actually be a formal charge because it got rid of the bond, right? It should be a formal charge of +1, and the oxygen here would have a formal charge of -1. And you can see how in total they end up with a net of 0, but when you put it in water and dissolves, you can now see the formal charges come out of it. So, with that being said, let's move on to the question number 16. We have, how many valence electrons does barium have, and what energy level do they occupy? So, barium, valence, and what energy level? So, with that being said, we're going to look at the periodic table, okay? And we first have to find barium. Barium is right here, okay? It is on the 6th, sorry, I'm blanking out, 6th row, okay? And it's on the 2nd column. So barium, this case is on the 2nd column, would have 2 valence electrons. And at what energy level? Okay, it's actually answered by the row it's in. It's going to be in the energy level 6, well, the 6th energy level. So for these type of questions, by finding out the row it's in and the column it's in, you should be able to theoretically find how many valence electrons and what energy level it's in. The tricky part is if you ever ask this for transition metals, because it's not always face value. But for columns 1, 2, and 13 through 18, it's relatively straightforward. how many valence electrons they have, and what energy level they're at. So just to review, the valence electrons is found by the column they're in, and the energy level is found by the row that they're in. Okay? So let's see what we have for choices. 1 valence electron in the 6s state. No. 2 valence electrons in the 6s state. Yes. No valence electrons? Definitely a no. So the answer here is B. B best describes barium. Well, that was a nice alliteration. And so for this one, they just went ahead to do the whole electron configuration. And they do end up with 6s2, which is what we can see actually by just doing the row and columns. And as you can see here, therefore the answer is B, 2 valence electrons in the 6s state. And this is what I mean in regards to, I guess, getting that extra help for transition metals. For transition metals, if you're not sure, draw the electron configuration and try to piece it from there, because they do actually help a lot trying to figure out what the valence electrons at least is going to be. Because the energy level is relatively straightforward, because it'll still be in a certain row, but the actual electrons, that's when you would involve the electron configuration, just to really see, okay, how many electrons are actually on the outermost shell. And now for question number 17. This one's asking us, is O2 polar or nonpolar? So, funny enough, there's many ways to approach this. Okay? But the best and most direct way is to just go to our electronegativity comparisons. These are both oxygen. They have the same electronegativity. The electronegativity difference in O2 would be 0. Even though it has lone pairs, so if you were to draw the Lewis structure, you see that it's double bonded to each other. Okay, and it looks something like this. Because the bond itself is nonpolar, because of the fact that oxygens both have the same electronegativity, we just say O2 is nonpolar. We need an electronegativity difference, well, great enough electronegativity difference, so typically something greater than 0.4 for us to say, okay, this is polar. And because we're dealing with the same exact atoms for each side, it's a difference of 0. So that's why this here is just going to be the answer of non-polar. So, the bonded atoms are both oxygen. There's a pull is equal strength. As a result, no charge separation, and the molecule is considered non-polar. This is correct. And now for question number 18. We have select the best Lewis structure for ClCN. So something cyanide, maybe chlorine cyanide. That would probably be the name of this. Nonetheless, though, let's see what we can select based on this. So what I like to do is actually just draw out my own Lewis structure and then compare. Okay, best Lewis. The trick here is that with, I guess, these type of molecules, what you are seeing are probably just resonance structures of this. So these are all technically most likely viable Lewis structures, but the best Lewis structure, we find that out by seeing which one has the least formal charge differences. We want as many formal charges of 0 there. So for this, chlorine is going to contribute 7 electrons, carbon 4, nitrogen 5. So 7 plus 4 plus 5, 16. So 16 electrons total. Carbon will go in the middle because carbon has the most unpaired electrons. So we're going to have chlorine on one side, nitrogen on the other. Okay, and now chlorine, based on its octet rule, is sharing one of its 7. So it's going to be 2, 3, 4, 5, 6, 7. Nitrogen is right now sharing one of its 5, so it'll be 2, 3, 4, 5. And carbon is sharing 2 of its 4, so 3, 4. So with this, there are now 4 unpaired electrons, 2 each. So what I would do actually is just throw them all into here to form 2 more bonds on top of each other. So that's going to end up with a triple bond. So if I were to redraw this, it would be chlorine, carbon, nitrogen. And nitrogen still has that. Carbon is done, and the chlorine would still have this. Now, with that being said, sorry, let me just fix that up. We have, in total, how many electrons? So we have 8 electrons from the bonds, because there's 4 bonds. And then we have 1, 2, 3, 4 lone pairs. So that's also 8, so we do have 16. So the electrons, perfect. Now let's see which is the best Lewis structure, based on the formal charges and also following the octet rule. So chlorine, typically formal charge 0, has 3 lone pairs and 1 bond, so that's check. Carbon has 4 bonds for it to be neutral, or that's charge of 0, which is also what it's doing. The triple bond counts as 1 bond each. Now the nitrogen has 1 lone pair and 3 bonds, which is also what this nitrogen is doing, because the triple bond counts as 1 bond each. Now with all this being said, I just happen to draw the best Lewis structure, but I could have also drawn it like this, for example. So still 8 electrons, okay? But let's look at the formal charges. Carbon stays the same because it still has 4, but nitrogen now has this. 2 bonds and 2 lone pairs. It turned a bond into a lone pair. So that would actually change its formal charge to be -1. Okay, so that's a -1 right there. And the chlorine also now has the same thing. It lost a lone pair and got turned into a bond. So that would actually mean it's +1 compared to what chlorine typically is. So although we still have a net of 0, this is still a viable Lewis structure. The issue here is that it now has not as many 0 formal charges. It wants to be as close to 0 as possible. So that's why, although this technically works, it doesn't really work in this case. So with that being said, we can look at all these answers and see which one works and doesn't. Okay, so this one for C, for example, has way too many electrons. That one just doesn't even work. Remember, we still want 16 electrons. Same thing with D if you look at it, okay? D has 1, 2, 3, 4, 5, 6 lone pairs. That's already 12 electrons. And then we have, oh wait, no, this works. Wow, just the electrons. So all of these are possible, I guess. Well, I don't know about C actually. C definitely looks like it has too much. Because let me count out slowly just to make sure. Yeah, because D, if we have 2, 4, 6, 8, 10, 12, okay, and then 1, 2, 3, 12 plus 6, okay, yes, that is off. That is 18. So D doesn't work because it actually has 18 electrons there, even though we only have 16 to work with. So D is incorrect. And same thing with C, because C, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 lone pairs, that's 16 electrons already. And then 2 bonds, already too much. B is what I drew here. And although technically it can pass, it wouldn't be the best option. And E is just like an inverse of D. And we already discovered that D had too many electrons. So A is the only viable choice here, because this is the best Lewis structure we can draw from ClCN. The best Lewis structure is A because they obey the octet rule, and the formal charge of all of them is 0. So this is correct. Now let's move on to question number 19. What is the Lewis structure for C2H3Cl? Show all unshared electrons. So for this, I thought I changed it to black. There we go. Lewis for C2H3Cl. So for this, let's just see how many electrons we're working with. Carbon, each carbon is 4, so that's 8 electrons. Hydrogen, that's 3 of them, and each hydrogen is 1, so that's plus 3. And chlorine, that's 7 because on the 17th column, okay? So 8 plus 3 plus 7. That is 18 electrons we're working with, okay? And now let's draw it out. So carbon, considering that it's has the most unpaired electrons, those two will go in the middle. Okay, so we have C, C, then we have H, 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 C, L. Okay, so now let's see what we can do. So chlorine right now should have 6 more electrons because it's sharing one of its 7. So that's 2, 3, 4, 5, 6, 7. And carbon, on the other hand, now this one should have at least 1 more electron on each one because right now it's sharing 3 of its 4. So 4 and 4. Now because we have 2 unpaired electrons, we're going to now throw them into the bond to form 1 more bond with each other. So that is why we get now C, C, H, C, L, H, H. And now let's verify that we actually do still have 18 electrons. So right now we have 1, 2, 3, 4, 5, 6 bonds. Okay, so that's 12 electrons. And then we have 3 lone pairs, so that's 6 more electrons. So that is indeed 18 electrons. So that's perfect. Now, we want to see if we actually kept the formal charges as 0. So for a 0 formal charge for carbon, it's just 4 bonds, which is what it's doing here. The double bond does count as 1 bond each, so it's perfect. The hydrogen is just 1 bond, okay, which is what every hydrogen is doing there. And the chlorine, okay, is going to be 3 lone pairs and 1 bond. So that is perfect, okay? With that being said, if we look at this then, the Lewis structure for this is indeed going to be just that. And we are showing all the unshared electrons. They would all be on the chlorine, okay? And so, that's what we're given. This is the Lewis structure. We're thinking this is more like the, I wouldn't really call this the Lewis structure. I did forget the name of this. But Lewis structure, typically they want you to label everything as such. This is kind of like if you're drawing out the, I guess like hydrocarbon. Technically, this does have a name. It's just skipping my mind right now. It's something like chloroethylene, something like that. Because this is 2 carbons. But point being, and it's a double bond, which is why we have the E and E ending. But the overall point is that this indeed will be the Lewis structure. Okay? This is correct. And now, let's see what we have for question 20. The last question of the day. Okay? And now, we want to answer the following questions pertaining to the Lewis structure below. So this is boron dihydrogen, okay? So boron, technically it is one of those metalloids. We really don't know what these things do, but we can just say it's boron dihydrogen, and it's 2-, okay? So, funny enough, boron is on the 13th column, so that's why it has 3 electrons it can use. And hydrogen only has 1 each, so that's 3, and then 1 each, so that's 3 again. but it is Bh3 minus, so that's plus one more electron. So in total, we're actually working with 7 electrons, which is a very strange, oh whoops, I miscounted, Bh2 minus. So that's a 2, so that's 3 plus 2 plus 1, 6 electrons. Apologies for that. So they did give us the electron, the Lewis dot diagram, so that's going to be, as they see there, boron in the middle, and then 2 hydrogens. And as you can see here, when we actually do the, I guess, the formal charges, boron, okay, likes to just have 3 bonds, okay? So if you replace a bond with a lone pair, so that's what we did here, this is actually how we got into a negative formal charge. And that's where the formal charge negativity will be for it to be the Bh2 minus. It's on the boron, actually, not the hydrogens. Because the hydrogens are fine. They just like to be like just one bond, which is what they're doing right there. So with that being said, the electron pair geometry around the B atom in Bh2 minus is, so electron pair geometry based on the central atom, we have to circle the amount of pairs it has. It has 1 bonding pair, another bonding pair, and 1 lone pair. So in total, we have 3 pairs. This is known as sp2 hybridized, and for this shape, we say that it's a trigonal planar. Okay, that is what we say when it comes to the electron pair geometry. All right. Now, how many lone pairs are there? There are, as we said, 1 lone pair. So the geometry, now that you're referring to the molecular geometry of Bh2, this will be known as bent, I believe, to where it's not a perfect trigonal planar where everything's 120 degrees apart. It's actually now the hydrogen just slightly close to each other, so just a little bit less than 120 degrees. And we actually check the Vesper theory sheet here just to make sure. So it's 3, and it's a 2-1 split, and it's also known as bent. So that's what we're looking at right here. Okay? So that is what we have for the molecular geometry of Bh2 minus. But now we have Bei2, so beryllium iodide, because I believe beryllium is a metal. Yes, it is. So it is just beryllium iodide. And they did give us a Lewis structure. We just like to verify. Beryllium can contribute 2 electrons. Iodine, 7 each, because it's on the 17th column. So that's 14. So that's 16 electrons total. And as I drew it there, the Lewis dot diagram is just Be, 2 bonds, and then the I's on each side. And they're all filled out the octet. Okay, and do you have 16 electrons? Let's see. We have 2 bonds, so that's 4 electrons, and we have 6 lone pairs, which is 12 electrons. So we do indeed have 16. So now, let's see here if it follows the formal charge. So beryllium just likes to have 2 bonds. So that's exactly what it's doing. And the iodine likes to have 3 lone pairs and 1 bond, which is what it's doing as well. So that's why the formal charge of this is 0. So now, as a last part check, we want to find out the electron pair geometry, how many lone pairs, and what's the molecular geometry of it. So we circle it now. We have 1, 2. We have 2 pairs. Okay? So this is just sp hybridized, and this actually just known as linear. Okay? And funny enough, because there are 0 lone pairs around the central atom specifically, so not the iodine, the beryllium, the geometry, the molecular geometry actually stays as linear as well. That's actually what all we do for this question. So now let's go down and see if that is the case. We have boron has 1 lone pair and is bound with 2 other elements. So the electron geometry is trigonal planar. Perfect, so that one we got. And because there's 1 lone pair, it's going to be bent. So it's perfect. The electron pair geometry around the beryllium is linear, as I said, and there's 0 lone pairs, so the molecular geometry stays linear as well. So luckily we were able to get the same answers as everything else. Hopefully you're able to see why. You have to make sure you count the pairs, that's why I circled them, okay? And based on that, you want to make sure you distribute them based on what they have. So of the pairs I counted, how many of them are lone pairs and things like that, etc. So with all that being said, this is correct. I do believe this is our last question for the day, but let's double check. Let's see. So it was indeed. So with that being said, I just want to thank you again for joining me today. I hope you have a wonderful rest of your day. Have a good morning. And for all the topics that we covered today, if you just need some extra help, definitely check out one of our professional tutors here by checking out the links in the description below. And anything else? No, I don't believe so. So thank you again for joining me. You have a good rest of your day, and see you next time.